We have an example problem here. A proton moves from point A to point B under the influence of an electrostatic force only. At point A, the proton moves with a speed of 50 kilometers per second. If the potential difference, VB minus VA, is negative 20 volts, what is the speed of the proton at point B? The mass of a proton is 1.67 times 10 to the negative 27 kilograms. All right, so I'm going to do a little sketch here. So my point A, my proton I know is moving at 50 kilometers per second. Point B, we want to know how fast it's moving. We're told that the electric potential or voltage at point B minus the potential at point A is negative 20 volts. So A is my initial, B is my final. Since the way this is worded is VB minus VA, this negative 20 volts is delta V. Now, to relate delta V to speed, probably the easiest way to go about that is conservation of energy, where the change in kinetic energy is equal, got a lag, negative change in potential energy. We know potential energy for electric potential energy anyway is Q delta V. So we can put in 1/2 mv final squared for the final kinetic energy. Delta K would be the final kinetic energy minus the initial kinetic energy. And again, I'm writing my V's for speed somewhat cursive-y so that I do not confuse them with my V for voltage or electric potential. So we know the mass of the proton, we know Q, the charge of a proton, so ultimately V final is our only unknown. So if we bring, actually I'm going to multiply this right-hand side first by 2 and divide by m, because that will leave me with V final squared minus V initial squared on the left side. So coming up here, V final will be this negative Q delta V over M plus V initial squared. Computer will catch up. And then square root of all of that. Charge on a proton, the fundamental unit of charge, we can get off the test notes. Delta V is negative 20 volts. The mass of a proton they gave us in the problem. And the initial speed they gave us in kilometers per second. We do need that in meters per second. And then plugging this all in. so that, sorry, it's taking me a minute to plug this in. So this is what I'm getting. This is in meters per second. Putting it back in kilometers per second, this would give me 80 kilometers per second, since I have to round the 9. Now let's make sure that makes sense. So we don't have an equation for like a constant electric field, but if we think about, just to make sense of this, we know for a point charge, the electric potential would be kq over r. So this proton, if it moves through a potential difference that's negative, V final minus V initial, that is negative 20. That means V final has to be less than V initial. So suppose this potential difference was created by a point charge, just to reason through it. The only way V final could be less than V initial is if R is bigger. So if we have a positive charge creating an electric field, we're essentially saying that our final location would be farther away than our initial location. So this means our proton moved in the direction of the electric field. Well, if this is a point charge, we know a proton is repelled and it should speed up as it moves farther away. So getting a final answer that's bigger, the 80 kilometers per second versus the 50, is a good thing. So this should be reasonable. It is good to make sense of that and just make sure speeding up or slowing down, if you were to solve a problem and it slowed down, just made sense in that situation.